Hello friends, in set relation functions till I have talked about the sets, subsets, operations on sets, and then Cartesian product of set, the relation, reflexive relation, symmetrical relation, transitive relation, and the relation which is the reflexive, symmetric, transitive, which is called as equivalence relation. We also proved that every equivalence relation on non-empty set X defined on set X defines a partition of that set, and conversely every partition gives rise to some equivalence relation defined on it. Today we'll take more examples on equivalence relations. Okay. So the first example, let n be positive integer, n greater than 1 be fixed positive integer, if I take n greater than 1, doesn't matter. Then for AB belongs to Z, for AB belongs to Z, A is related to B if A minus B is divisible by n. A minus B is divisible by n. This is equivalent to A minus B is multiple of n. Equivalent to A minus B is equal to nk for some k belongs to Z. Two integers are related. Two integers are related if their difference is multiple of n, difference is divisible by n. Is it clear? So that this relation is equivalence relation on Z, find describe equivalence classes. Equivalence classes. So, what to check whether this relation is reflexive, symmetric, transitive, etc. Solution. First, reflexivity. Means what to show that every integer is related to itself. Okay. Means it is multiple of n. That we have to show. So for any a belongs to Z, a minus a is equal to 0, and this is 0 is nothing but 0 into n. 0 into n. Is it clear? So a minus a is multiple of 0. Or you can write, if it is just task, it is divisible by n, then you can write 0 is divisible by n. 0 is divisible by n. Right? So implies a is related to a, and there is no any restriction for any choice of a, and therefore this is the reflexive relation. Second, symmetry. Let AB belongs to Z be such that A is related to B. For symmetry, we have to show that whenever A is related to B, then B must be related to A. Then A minus B is equal to nk for some k belongs to Z. If you write in terms of divisibility, A minus B divisible by n, then n divides A minus B, and therefore A minus B is multiple of n, and then you will get this step. Okay, now I am taking equivalence step for that directly, and therefore b minus a is equal to n into minus k, for minus k belongs to z. Therefore b is related to a. Thus a related to b implies b is related to a for any a belongs to z. Whenever we take any two elements in Z such that A is related to B, then B must be related to Z. And therefore, this relation is symmetric relation on Z. Now we have to check whether it is transitive or not. So simple task. Third, transitivity. So let ABC belongs to Z be three integers such that A is related to B and B related to C. What that implies is the differences are divisible by n, means they are multiples of n. Okay. Therefore, A minus B is equal to some multiple of n, that is nk1, B minus C is equal to nk2, or some k1, k2 belongs to Z. For some k1 and k2 belongs to Z. This, now A minus C, I can write it as A minus C is equal to A minus B plus B minus C. But A minus B is same as nk1 and B minus C is nk2. So this is nothing but n into k1 plus k2, where this k1 plus k2 is also integer. So this implies A minus C is multiple of n because it is integral multiple of n. Okay, and therefore A is related to C. Thus A related to B, B related to C implies A is related to C. And therefore this relation is transitive relation on Z. From 1 to 3, it is reflexive, symmetric. 1, 2, and 3. Okay, I have given this numbering till is equivalence relation on Z. Once it is equivalence relation, then we have to find out their equivalence classes. We have to describe equivalence classes. Equivalence classes. For 0 belongs to Z, equivalence class of 0, which is denoted by this symbol or 0 bar, it is set of those x belongs to Z such that x is related to 0. Means x belongs to Z such that x minus 0 is equal to nk and k belongs to Z. X minus 0 must be multiple of some nk, which is nothing but nk, where k varies in Z, and this Z is precisely, if I put k equal to 0, I will get 0 here, k equal to 1, I will get n, k equal to 2, I will get 2n, and so on. On this side, I will get minus n, minus 2n, and so on. Is it clear? Remember, if n equal to 1, then equivalence class of 0 is nothing but 0, 1, 2, minus 1, minus 2, and dot dot etc. If my choice of n is 1, then x minus 0 is equal to 1 into x, right? So every integer is multiple of 1. Every integer is multiple of 1. Is it clear? So every integer must lie in equivalence class of 0 there. Equivalence class of 0. And in that case, if I have n is equal to 1, then equivalence class of 0 will become 0, 1, 2, minus 1, minus 2, and so on this side. This is precisely set Z. Precisely set Z. And we know that every equivalence relation partitions the given set. Partitions the given set into equivalence classes. As just single equivalence class covers the whole set Z, so there is only one equivalence class. We also know that X belongs to or Y belongs to equivalence class of X if and only if equivalence class of Y is equal to equivalence class of X. Means as for n equal to 1, equivalence class contain all integers, so equivalence class of each integer is equivalence class 0. Is equivalence class 0. So there is just only one equivalence class when n is 1. When n is 1. So I am not taking n to be say 5 or 7, 8, 12 and so on. I am just taking any n greater than or equal 1. So if n is 1, there is just single equivalence class. So I am not taking any restriction on that. If I take now 1, then it is equivalence class contains X belongs to Z such that X is related to 1. Means X such that X minus 1 is equal to 2K, K belongs to Z. And then this is nothing but X is equal to 2K plus 1, where K value is in Z. Oh, sorry, X minus 1 is equal to NK here, not 2K, so NK. Now, substitute again K equal to 0, I will get 1, then K equal to 2, we will get 2n plus 1, right, 3n plus 1 and so on. On this side, it is for K equal to 0, we are getting 1, K equal to 2, 2n plus 1 and so on. Where is yes, what is happening here? 1 is getting added here, 1 is getting added here. The next element is n, sorry, K equal to 0. What I am getting for K equal to 0, it is 1. For K equal to 1, it is n plus 1, sorry, n plus 1. For n equal to 2, 2n plus 1 and so on. On this side, minus n plus 1, minus n plus 2, minus 2n plus 1 and so on. If I take 2 now, if I take 2, similarly equivalence class of 2 is equal to, this middle element will become 2, then n plus 2, 2n plus 2 and so on. Here minus n plus 2, minus 2n plus 2 and so on. We'll get this. Is it clear? Means just this is shifting by 2 there and so on. If I take equivalence class of n minus 1, then I will get your, here middle element will become n minus 1, 0 is getting added there. Then if I add n minus 1 here, n minus 1 plus n, that is 2n minus 1, n minus 1 plus 2n, 3n minus 1 and so on. On this side, n minus 1 n minus 1 minus n. So it is minus 1 here. Okay. Then minus next element minus 2n plus n minus 1. That is nothing but minus n minus 1. We'll get this. Now, if I take equivalence class of n, see here, n is here, equivalence class of minus n, equivalence class of 2n, and so on. Equivalence class of 2n plus 1, second one, n plus 1. Is it clear? Equivalence class of minus n plus 1 is same like this. So if you observe here, it contains 0, then 1, 2, n minus 1. Next element, central element will become n there, n. Is it right? And then in that n on this side, if you add minus n plus n, that gives us 0 again. This set is just repeating there. For next element n plus 1, we will get next set, and so on. So here, union of equivalence class of I is equal to 0 to n minus 1 is equal to z, is equal to z. Is it right? And equivalence class of I, intersection equivalence class of j is phi for 0 less equal I less than j less equal n minus 1. Therefore, set of all equivalence classes is nothing but 0, 1, 2, and so on, n minus 1. Later on, we are going to denote this by 0 bar, yes, 1 bar, 2 bar, and so on, n minus 1 bar. This set, we are going to denote it by Zn. We will denote it by Zn symbol, okay, for further study. Is it clear? Next example. For a comma b belongs to Z, a is related to b if a square plus b is even integer. A square plus b is even integer. If I take this one, okay, is tilde equivalence relation? If so, describe equivalence classes. So first, for a belongs to Z, a square plus a, I can write this as a into a plus 1. A into a plus 1 is product of two consecutive integers, in which one must be even. And therefore, a square into a square plus a is equal to a into a plus 1 must be even, is even. Even integer into any other integer must be a even integer, okay? And therefore, A is related to A for any A belongs to Z. And therefore, tilde is a reflexive relation on Z. You put a second, so symmetry. Let AB belongs to Z be such that A is related to B. Therefore, A square plus B is even integer, is an even integer. Therefore, A square plus B is equal to say 2k for some k belongs to Z. As it is even, therefore it is multiple of 2. Now, we have to check whether B square plus A is even or not. So, B square plus A is equal to, I can write this via A square plus B square. So, I can write this is equal to B square plus A square plus B. I don't want A square and B here. So, I will write it as in terms of minus A square minus B, minus A square minus B. Is it clear? If you take this number in this form, B square plus A and plus A, then how will you write it? How can write this? If you see here, B square plus B, A square plus A, and minus A square minus B. Okay, so I can write this as B square plus B, B square plus B plus A square plus A minus A square plus B. Is it right? See here, A square get cancelled, this B, this get cancelled. Now, B square plus B is nothing but B into B plus 1. This is nothing but A into A plus 1. And this is your 2k from 1. Again, these are consecutive integers, consecutive. Therefore, this is say 2k1 plus 2k2 minus 2k for some k1, k2 belongs to Z, which is equal to 2 times k1 plus k2 minus k, where k1 plus k2 minus k belongs to Z. Addition and subtraction is integer, and therefore B square plus A is even integer. Is even integer. Now, we have to check whether it is transitive. Third, transitivity. So let ABC belongs to Z be such that A is related to B, B related to C. Then A square plus B, B square plus C are even integers. Therefore, A square plus B is equal to 2k1, B square plus C is equal to 2k2 for some k1, k2 belongs to Z. They are even, so we'll get this. Now, A square plus C But relate them via b square plus c. Right. So I'll write this as a square plus b, a square plus b plus b square plus c. So I am getting a square plus c here minus, I want only a square plus c, minus b plus b square minus b plus b square, right? So this is equal to 2k1 plus 2k2 minus b into b plus 1 again, b into b plus 1 consecutive integers. So one of them must be even. So this is 2k1 plus 2k2 minus 2k for some k belongs to z, which is 2k1 plus k2 minus k, and k1 plus k2 minus k belongs to z. Therefore a square plus c is even. Thus a related to b, b related to c implies a is related to c, and therefore it is transitive relation. Therefore tilde is transitive relation. On Z. So from 1 to 3, 1, 2, 3, this symbol is equivalence relation on Z. Equivalence classes. Equivalence class of 0 is equal to set of A belongs to Z such that A is related to 0. Means your A belongs to Z such that A square is even integer. A square plus 0 is even integer. What will be this set? Set of those A for which A square is even integer. A square A is even integer. If I take 0 square is 0, 2 square is 4, 4 square is 16, 3 square is 9, 1 square is 1. So A square is even means your A must be even number. Your A must be even. Is it right? So it is nothing but set of even integers. All even integers. If I take equivalence class of 1 now, A belongs to Z such that A is related to 1. A belongs to Z such that A square plus 1 is even. So this must be set of odd integers, set of all odd integers. Now equivalence class of 0 union equivalence class of 1 is Z, and equivalence class of 0, 1 are disjoint. Therefore, these are only two equivalence classes under defined operation. So, in this lecture, we have only studied two examples. You can define so many equivalence relations on set of integers. For your practice, we'll take few more examples. And as equivalence class is important for us while studying the congruence relations on Z, that's why I have not talked about what is meant by antisymmetric relation. So in next lecture, I will also introduce what is meant by anti-Semitic relation on site, and with help of that anti-Semitic relation, I will also talk on partially ordered relation defined on set. So equivalence relation, partial ordered relation, and we'll distinguish the two relations on sets. So with this discussion today, we'll stop here. Stay at home, be healthy, good day, bye bye.